Morning. What's up? Yeah, we're gonna have class in here instead. It's a better classroom. Sit wherever you want. Was anyone else at the other classroom or? Yep. Well, I threw it on Discord. If anybody's on. We'll give one a minute, see if anybody shows up. No, it's just gonna be you and me though. You have anybody's contact info? Yeah. Yeah. That'll happen. We'll give them a couple more minutes. I know a couple people on Discord said they're on the way. All right. What's up? Figured. That's figured. Obviously, two to a pod, guys. Two to a pod. So where we are.
No, I went to go to the bathroom.
So we're just missing Connor, right? All right, guys, let's get started. Lord, thank you for bringing us together this afternoon. Thank you for all the blessings in our lives. We pray that you would continue to help us focus the rest of the semester, get used to some of the interesting protocols that we have to get used to, and just help us to thrive in this setting. In your name we pray. Amen. All right. So we're back. We're in class, right? Still taping stuff that will go on YouTube. That's why the Zoom thing is on, right? So you guys know. Hopefully the microphone picks things up. We'll see what happens. If the video stinks, then let me know. All right. So what are we doing today? All right. This, right? Angular momentum. So recapping last class, right? Angular momentum, everything practice. All right, so angular momentum, right? We watched that video at the end of class on Friday, right? What do we need to know about angular momentum right now? Is that for a particle, each particle will not have angular momentum on its own, right? We don't talk about particles rotating. We talk about particles translating. However, if I'm standing here, right, and there's a particle that's spinning around me or moving past me, right, that's going to have angular momentum as considered from my point of view, right? And that's what we're talking about with angular momentum, right? That was the point of the video, was you can't take the angular momentum of a particle unless you know where you're taking it about. It's the same idea as you can have a torque on something, right? But it matters where I have my pivot point, right? If I push here, this is going to be a much stronger torque than if I have my pivot point at the center of the pen, right? So it's all about where are we taking angular momentum about. For our purposes right now, we're going to see how this links into systems of particles, right? So if I have a group of particles moving in a series, right, or moving about a certain point, we can take the angular momentum of a system of particles. We'll talk more about that later. But what we're essentially using angular momentum for is to get ourselves another equation if we need it. Angular momentum allows us to relate the velocity of a particle, right, or the angular velocity of a particle to our equations, right? Because momentum is just mass times velocity, and angular momentum is just mass times velocity times the distance that we are away from wherever we're interested in taking angular momentum. We need to talk, well, we'll catch up with some of this stuff later. Everything is going to take a while, so we'll just kind of hopefully catch it on the fly. If you guys need to ask questions mid-lecture, please do. Do you guys have any other major things that you want to bring up now before we move on to some other stuff? No? Everybody's all right? Okay. Okay, so what do we got? These are the things that are due, right? We did our VOT assignments, homework, and learn smarts this weekend, right? Let's make sure we get those done. Let me know if there's any issues with the McGraw-Hill homework. Let me know if you have any questions about the homework. Right, I got office hours after this class from 3 to 5. Make sure you're using the office hour link, right? So it's like first or second announcement for this class all the way back. So you might have to go on to another page of announcements to catch it, but there's a separate link for office hours because all office hours are through Zoom, right? All right, so let's warm up by doing this problem together, okay? We'll do this one together. So I really like this problem a lot. It's a direct quote from me. So you guys, hopefully you guys know professor speak, but when you hear professors say like, I really like this a lot, or I think that this is really important, right? Then we should probably pay a lot of attention to this problem, right? Because this is something that I really like. All right. So what do we have? We've got two blocks, right? These two blocks are connected by a cable around this pulley, right? One's 100 kilograms, one's 300 kilograms. What do I want to do, right? I want to determine the acceleration of each of these blocks. So how should we do that, right? We're also told some key things here, right? That it's on the horizontal plane or frictionless, and the pulley is assumed to have negligible mass, right? So it's a massless, frictionless pulley. Okay. Didn't mean to do that. Right? So what's the first thing that we need, right? We should probably start with the three body diagrams, right? Because what's the key here? What are we asked to find? Well, we were asked to find acceleration. How are we going to find acceleration? Well, what we have in our toolbox right now, we can either do a kinematic equation, right? Or we can use Newton's second law. Those are the two main things that we have in our toolbox right now. This in particular, since we're given masses, means we can get weights. We're going to use Newton's second law, right? So we need free body diagrams, right? So we're going to have to draw a free body diagram for A and a free body diagram for B. So as you guys take a couple minutes and draw your diagrams. Right? Couple more minutes. Then we'll talk. Gives once more time, we're good. Okay, free body diagrams, right? All right. You have more time if you want more time. Guys. Yeah, I'm here till 3, so I prefer not to spend all day on this, but you can. All right. Since nobody seems to want more time, we need free body diagrams, right? So I've drawn boxes around these two, right? So think about that as kind of like our control volume, right? When I say control volume, these are the bodies that I want to isolate, but there's one more here, right? And we'll talk about it in a second. So if I'm going to draw a free body diagram for A, what's that going to look like? What is that going to look like? Remember, it's frictionless on the horizontal plane, right? So what forces would you expect to be acting on A? What do you guys think? What did you have? Sure, right? You're going to break this cable, so you need the reaction tension from there, right? You can assume that this is pulling downward, sure, right? Because we would imagine since this is heavier, this is going to pull the whole thing to the right, right? So yeah, okay. What other forces are acting on A besides that tension? Normal force from touching the ground, right? And one more. Yeah, weight, right? The weight of the block itself. We know there's no friction, right? So we don't have to worry about that. What about here? What are we looking at here? Now, it's not easy to see, but it's not touching it, right? It's not touching the wall. It's just hanging there. So what do we expect as forces on this 300 kilogram block, on block B? We got, yeah, right. So what would be pulling it down? Was that? Yeah, it's weight, right? It has some weight. All right, and what's stopping it from going down? Tension, right? So you've got some tension here, and you've got some tension here. All right, so let's look.
We have a normal force
On the block A, yeah. All right, so like we thought, right? We've got our normal force and our weight and our tension. Right here's our kinetic diagram. We're going to assume that we're not accelerating up off the ground, right? Notice for block B here, we've got the weight and we've got the tension. I've called these out as different tensions, and there's an important reason for that. Let's go back and look. Go back and look. Notice this cable goes around this pulley, then around this pulley, and then back up. It doesn't ever connect to block B. What connects to block B is a separate cable attached to that pulley C. So the way that cable tension works, right, is that if you have a cable, it's the same tension no matter where you are on that cable, right? That's just how cables work. So this tension here is the same as this tension here, is the same as this tension here. But it's different than the one that's connecting that, right? So we need a free body diagram for the pulley, right? And we were told that that pulley was massless, so we don't have any weight. All we have is the tension coming down that's holding, that's from that block pulling down on it, and the tension pulling up, which is from block A, right? This is one of the keys to this, right? Because this allows us to equate the tension T1 to T2, right? And because there's no mass, the sum of those forces is equal to 0, right? So those forces are in static equilibrium. We'll see that in a second. All right. So far, so good. Everybody doing all right? We can draw a kinetic diagram for this if we want. It's going to be uninteresting because there's no mass, there's no inertia, so everything's equal to 0 on the kinetic diagram, right? So that's why I didn't draw it. just that everything's equal to 0. Everybody okay with this so far? All right, just the free body diagram. I will tell you this, free body diagrams or your diagrams in general are going to be one of the most important parts of doing these problems. And it's where I tend to score the most points. So don't forget them, right? When we're doing the quizzes, and right, don't forget to draw a free body diagram because you're going to lose a ton of points just for not having them. You want to have them. You want to have them. You can ask former ESG 360 students, right? They will tell you that I'm not joking around. These are super important. We need to be able to do these diagrams, okay? So don't be like some other students and allow yourself to hemorrhage free points, okay? Just for drawing some free body diagrams. If you're still confused about free body diagrams, that's fine. Come to office hours and we'll talk about them more, right? This is not the last time we're going to talk about them the whole semester, right? We're going to go through another activity in a few weeks when we get to rigid bodies, and we'll go over how to do free body diagrams again, just because they are so important, especially when we get to rigid bodies. So, where do we go from here, right? Well, let's write some equations, right? We'll start with block A. Right, so if I write Newton's law for block A in the x direction, I can sum my forces in the x direction, right? And what forces did I have? Well, I had the tension. That was it. Everything else was x direction or y direction, right? Let's go back. Remember, because there's no friction, the y direction isn't really helpful in this one for us, right? This y direction here doesn't really help us. It's N is equal, normal force is equal to the weight, big deal, right? Not helpful for what we're doing. We need T1. T1's in the x direction. It means it equals the mass times the acceleration in the x, right? So that's our first equation here, right? A, acceleration of A in the x direction. I'm going to call it equation 1 for right now, just so we can keep track of them. And so this came from block A. Am I loud enough for you guys? I have to get used to, a mask and a face shield and my personal force field that extends to this yellow line and everything. So, okay. All right. Block B. If we go back to block B, what do we have? What's the sum of my forces here? Yeah, it's in the y direction. Right? So we'll have T2 minus weight of B. So I'll sum my forces in the y. That's equal to T2, which was positive, minus the weight, which was in the negative direction. And that's going to equal the mass of B times the acceleration of B in the y direction. And we'll call that 2. So we've got those two. And if we're looking at that, well, we don't know the tension T1, we don't know the tension T2, and we don't know the acceleration of A or the acceleration of B. So we have 4 unknowns and 2 equations. You have 4 unknowns, you need 4 equations, right? To solve it. Systems of equations, right? So where are we going to get these 2 other equations from? Well, one of them is going to come from our pulley, right? We're going to do a Newton's second law analysis on the pulley C, right? Which is why we do the free body diagram. What's this going to buy us? Well, this is going to give us a relationship between our 2 tensions, right? So if I sum the forces on that pulley, what do I get? What do I get? All right, so the sum of the forces is equal to 0, right? So if you add up those forces, what do you have? How many T1s do I have? So you get 2T1 minus T2 is equal to 0, right? Or you get, so let's write it. Let's write it here. And get this to work. So if we sum the forces in the y direction for C, we get T1 plus T1 minus T2 is equal to 0. Or if we use some algebra, we can get T1 is equal to 1/2 of T2. All right, well, that's cool. That got rid of one of our unknowns, right? So now we still have 3 more. We still need one more equation. How do we get that one more equation? This one, you're gonna have to dig deep back to probably like 2 weeks ago. 2 weeks ago. How are these systems, how are these particles, how are these blocks connected? How did we connect these here? How did we connect these? What are we using here? What is that? It's cable. Didn't we talk about how we can figure out how cables are moving, how system of particles are moving when we talked about kinematics? If I drew this as y sub b, right, this distance here, and this we'll call x sub a, wouldn't that be the total? If I added all those together, isn't that just the total length of the cable? Remember your shoelaces, right? Sometimes they're uneven, but that doesn't change the total length of lace that you have, right? So if I know the total length, right, I can say, remember, I can write down from cable kinematics, and I can take my cable kinematics, and I can say, well, I've got 2 times y sub b plus x sub a is equal to some constant length, right? But what I really need is it's something that relates the acceleration of A in the x direction to the acceleration of B in the y direction, right? That's what I need. So how do I get from this to acceleration? I take the derivative twice, right? And if I take the derivative of this twice, take d dt twice, I'll get 2 times a sub b in the y direction plus a sub a in the x direction is equal to 0. And that's our final equation. So I have a way to relate the 2 accelerations to each other. I have a way to relate the 2 tensions to each other. This is going to be my 4th equation. So this right here, this is the reason why I like this problem, right? Because it takes what we just learned about Newton's law and it incorporates something that we learned a couple weeks ago, right? That's still relevant. And this is this and the fact that we need a 3-body diagram of the pulley are the 2 things that break this problem open. Yeah, Logan. So if you take the derivative of position once, you get velocity. And then you take it again to get the acceleration. And acceleration is the second derivative of position. Okay. be nice if they invented one of these masks that was like comfortable on your ears. That'd be sweet. Whew.
What is that? That whole derivative right there.
Mhm.
I don't know how you go from that to that.
I mean, how do you go from that? How do you know to take the derivative there? Or
I mean,
how do you do the derivative?
we have to take the derivative. I'm trying to do the math right now.
So if you go from here to here, right?
Yeah.
This is 2 times, right? 2 is a constant, so we pull it out. We take the derivative of y sub b with respect to t, right? But that's a position, so that's really just the velocity of b, right? Then I take the derivative with respect to time of a, that's the velocity of a. Since it equals a constant length, this derivative, the derivative of c is 0. And then if we do it again, we get to the acceleration, right? So remember, if you take the derivative of position with respect to time, what are you doing? What are you physically, what is the quantity that we're looking at? We're looking at how the position of something changes with respect to time, right? So if I had it on a graph, right, this is my x position versus time, right? It's a bad graph. Start with the axes this time. So it's something like that, right? This describes my position as a function of time. What is the derivative? Well, the derivative is the slope of that line, right? How do we describe the slope of that line? Well, that's going to be the change in x, the rise over the run, right? The change in x over the change in time. If you do this for a single set of points, right, for a single portion of the line, right, you can do it like this. But if you wanted to know for everything over the entire function x of t, how would you do that? Well, you'd have to take the limit of this as time goes to infinity, right? And if you do that, that's how we get the definition of a derivative, right? So really what we're doing is we're trying to see how do the 2 sections, the 3 sections of this cable change throughout time, right? And we know that it's a constant length because your shoelaces, right? Your shoelaces will never, I can pull as fast as I want, right? But it will never change length, ever, right? This cable is connected, right? There's a fixed amount of cable that's there, right? So if we know that these sections will change at time, right? Because if I pull, this pulls down, right? At some point in time, A will be here, and this section, we'll call it X prime A, is going to be shorter. But these 2 sections, Y B prime, will be longer because this block is now down here. But the total amount of cable will still be the same. So those are our 4 equations. So what do we do now? Yeah, Zach, what's up?
I guess one of the things, so I guess one point that might be one is the way to block A.
Say that one more time.
But T1, why it's equal to mass A.
So remember, we're using Newton's second law, right? Which tells us that the sum of the forces, in this case in the x direction, has to equal the mass times the acceleration of the object in the x direction. We only have, if we're summing our forces, right, we only have in the x direction T1. That still has to equal ma sub x, right? We don't know what that inertial term is. So you can't assume that it's 0, right? Because the other side's pulling down. So the block, think of the inertial term as the minimum amount of force that you would need to generate to make it move, right? So the mass times the acceleration is essentially our inertia, right? It is something, you can think of it almost as something we have to overcome, okay? In this case, it's actually pulling on the object in the negative direction. It's pulling it downward, okay? So the way that Newton's law is constructed, right, this is why we do our free body and our kinetic diagrams this way, right? Remember, the free body diagram is equal to the kinetic diagram. And you piece it together just in the x direction or just in the y direction. You never cross, those things never cross, right? You never add y to x or x to y, only x to x and y to y. That's a vector, that's from vectors. We'll go more over vectors when we get to rigid bodies, because that's when they're going to really become more prevalent. Right now, the thing that we need to remember about vectors is that you can break them down into components, right? You can get them into x and y components. That's really what we need to be able to do. We need to be able to do the trig to get things into x and y components. Because we want to analyze things so that we can figure out the x direction acceleration here and then the y direction acceleration of the block. Remember, it's not in free fall either, right? This isn't in free fall. This block here is holding this back from being in free fall, right? Holding it back from being in free fall through that tension. That answer your question, though?
Well, yeah, that was mostly also, I guess like I initially assumed that T1 would have been related to like mass.
I mean, it is, if you look through this equation here, right, we're going to be able to, if we plug in for T1, right, or T2, you would end up, right, because we know that T1 is massive A times AX, right? So that means that T2 is 2 times the mass of A times AX, right? So it is a function of that. It's just not always 100% clear from just looking at it, right? So we're just double checking with our free body diagram to make sure that we're getting the right relationships. So T1 is related, right? If I go back and, if I substitute for T2 here, right, from my other equation, you'll get it in terms of the weight of B and the mass of B, right? And yes, it's going to affect how much tension we have, right? The heavier the weight, the more tension you wind up with. All right. So what do we do from here? Right? We're gonna do this the long way. We're gonna actually substitute it all out. Right? There we go. So let's substitute in for some of our variables, right? So in equation 1, we had T1 was equal to MA times AA. Well, the mass of A was 100 times AA in the X. Okay. For T2, I've got 300 times A sub B in the Y plus 300 was 9.81. All I did was I moved the weight over, right? I had tension minus the weight, now I moved the weight over. You can see that the tension is, in fact, a function of the mass and the weight of block B, right? I'm also going to say that T2 minus twice T1 is equal to 0, and that my acceleration of B is equal to negative 1/2 acceleration of A. Okay. So I'm going to number these just so we can reference them. Okay. So the first thing that I'm going to do is I'm going to substitute equation 4.1 into equation 2.1. So into 2.1, right? And if I substitute 4.1 into 2.1, well, I'm just going to take AB sub y, right? I'm just going to take this guy here, and substitute in for that, right? That's what we're doing. So our new equation is going to tell us that the tension 2 is equal to 300 over 2 times negative the acceleration of A plus 2,943, which is just 300 times 9.81. I just did that. Because as much fun as it is to write 300 times 9.81, right? You can just write 2,943. I'll call this guy 5. All right, is everybody with me so far, right? We're just going to start taking these equations and folding them into each other, right? Where do you think we go from here? Where do you think we go from here? We can do a couple of things. Yeah, Alexis. Good question. What we got here? Yeah, we'll do. I have that flip. Sorry. My bad. I mean, algebraically though, it doesn't make a difference in honesty, right? Because if I move both of those to the other side of the equal sign, you just get the same thing that I wrote otherwise, right? For example, right? If I subtracted 2t, right, from both sides, 2t1, I'd get negative 2t1, then I'd have to add, right? So algebraically, these two expressions are in fact the same, yeah? So either way, you'll get the same answer. You'll get the same answer. All right, so what I'm going to do is I'm going to take equation 5 and equation 1.1, and I'm going to sub both of those things into equation 3.1. Okay, so I know what T2 is. I'm going to plug it in for T2. I know what T1 is. I'm going to plug that in for T1 here, right? So let's see what happens if I substitute 5 and 1.1 into 3. Again, it doesn't matter if you which one is positive and which one is negative, right? We want to make it consistent with what we have. We can make that whole thing negative, right? It's the same thing. And look what happened. Now I've got one equation that just has a sub x, right? So I can solve this directly for a sub x, right? I'm just going to have to do some algebra, move some things around. Okay? And if you solve this for a sub a in the x direction, what do you get? 8.41 meters per second squared. And notice it's positive. That's important because that's telling us that we assumed correctly. We assumed that this would be moving to the right. And guess what? It's moving to the right. And our gut check tells us that makes sense, right? Because if I was pulling down, if I had a heavier mass there, I should be moving that block to the right. Okay. What do you do from here? Well, you're going to take this and you're going to plug that back in right here. So we're going to take that a sub a and plug it into equation 4.1. I'm gonna, so the next thing is plug AAX into 4 point. What's that telling me? That tells me ABY is equal to -1/2 AAX, which is -1/2 of 8.41, which is -4.2 meters per second. So we asked for the acceleration of the blocks and the tension. So now we have enough information to solve our tension equations, right? Because we had, let's go back and look at that. We have our tensions both as functions of those accelerations that we just found, right? So what do we have? We look here, right? T1 and T2 are together, or we can just plug in here. So either what you do is you take AAX and you plug in to get T1, and you take ABY and you plug in to get T2, or you find either T1 or T2 and then you use this equation to find them, right? So it doesn't really matter, you'll get the same answer. So let's solve for T1, right? Solving for T1, remember T1, so let me write down what we're gonna do. We're gonna plug AAX into equation 1.1. We'll get T1 is equal to 100 times 8.41, which is 841 Newton. Oh, sorry. There we go. That screen freeze always gets me. Always gets me. All right. So now we've got our tension T1 in that first cable. What about T2? Well, I'm going to use equation 3.1 to get T2, right? So I'm going to plug T1 into 3.2. Now I get 2 times 841 is equal to T2. So T2 is equal to 1,682 newtons. And I'm done. So notice, right, we had to use our kinematics to help us out here, right? And this is a common theme that we'll see as we move forward, especially when we get to rigid bodies. A lot of rigid body motion problems or finding forces comes down to us being able to figure out accelerations, right? Why is that? Well, the mass times the acceleration, that inertial term drives the sum of our forces, right? You guys have any questions on this? Take it step by step, right? That's my big advice here is do the free body diagrams, do Newton's law, right? See how many unknowns you have. If you need more equations, consult kinematics, right? Or is it a linked system, right? If it's a linked system, you can use our cable stuff, right? If it's not, it's a little trickier. But we'll talk about stuff like that later, right? For rigid bodies, it's going to be relative accelerations and relative velocities and things like that, right? But that's not for a few weeks yet. You guys have any questions on this? Yeah, Zach.
How come we don't do anything with the line diagram or anything
For
called that?
D.
Yeah, but you have the other goals.
Point, is that where the cable comes back and attaches? Oh, for the pulley itself. all you're gonna see if you do that is that the tension of one is equal to tension one, right? So, um, so we didn't do it. If we were asked to find the reaction forces at the pulley, like at that pin there, then yeah, we would have to do it there, but that's not something that we're gonna need for this class. So yeah, we don't do one at D because if you did, it would just be a trivial one. It's not wrong to do it, but you would just get T1 is equal to T1, right? Which is something that we kind of just know from how cables work, right? Any other questions? No? You good? Ooh. Man, if you just looked at this right here, you'd be like, what the heck is going on? But all right. So let's talk about potential energy, right? Last class we finished up, we were talking about angular momentum. We talked about how that could be potentially useful-ish. We just kind of did a derivation. We didn't really talk about it too much. It's not going to be super useful for right now, but we will talk about cases when it will be in a couple of classes. So let's talk about potential energy, right? Potential energy. What is potential energy? It's the amount of energy that we have that's stored in an object, typically due to a difference in height from some measured reference point, right? So in this case, the potential energy of the ball at the top of the path is transferred to kinetic energy as it meets the ground, right? We lose height, why? Because some of our energy is getting converted to sound when we hit, right? And heat from friction. So we lose energy with every concurrent bounce. So in the real world, right, real world problems, we will never, and you guys can test this, right? You get a bouncy ball and you drop it, it will never get back up to the height from which you dropped it, right? Because you're releasing energy and losing it to other forms. If work of a force only depends on the difference in position, we can express this work as potential energy. Okay. So, can the work done by the following forces be expressed as potential energy? Remember, the definition is only if we can express it as a function of the height, right? So, can weight do work? Can the work done by the weight be discussed as potential energy? You guys think? 50-50 shot. Throw your hands up. Who thinks yes? Okay. Who thinks no? Okay. Who's gonna wait it out and see if I just hit the button anyway? Yes, right. The weight. Think about this, right? If I drop the ball, right, the weight is what's doing the work there. It's the force that's causing. It's causing some that difference in height is what's causing me to store energy, right? The weight definitely stores potential energy, right? That's how we come up with the standard formula for potential energy, right? Mass times gravity times height. Well, mass times gravity is just weight, right? It's the weight times the height. What about friction? Can friction be expressed as potential energy? Who thinks yes? Who thinks no? No, friction cannot, right? What about normal force? Can normal force be discussed as potential energy? Who thinks yes? Who thinks no? Good job. What about spring force? The force of a spring, can that be potential energy? Yes or no? Sweet. So we already have some idea of what can do potential energy, what can store potential energy and what can't store potential energy, right? That's good. So the work of a force of gravity, or the weight, right, is expressed as U from 1 to 2. So our textbook uses U to talk about potential energy, capital U. The way we read this is we say the energy from 1 to 2, or sorry, the work from 1 to 2, right, is my potential work from 1 to 2, is defined as the weight times the distance that I am at minus the weight times where I'm at there, right? So if this is 0.1, this is 0.2, right? The weight of this block here minus the weight times the distance of the block that moves here gives me the amount of work that I've done, right? From 0.1 to 0.2. The work is independent of the path, right? So essentially, the amount of work you do, if you're going to go up a ramp or you're going to go upstairs, doesn't matter, right? It's all about the force that you exert through the distance that you've traveled. There's nothing to do with whether it's curved, whether it's stepped, whether it's flat, right? It has nothing to do with the actual path. Depends only on the initial and final values of the weight and the height. Okay, so the potential energy due to gravity, V sub G. Right? So in our book, we'll use V as potential energy and U as work. Right? V sub G, or you might see that sometimes I will write this as TE for potential energy, right? I'm not partial to the way that they describe things, but that's it. Is the weight times the height. Right. So the potential energy of a force or of a body with respect to the force of gravity is this. So the work done to get from point 1 to point 2 is a function of how my potential energy changes from point 1 to point 2. Right? And here we have the makings of the theory of, or the principle of work and energy. Right? Work and energy are related. How are they related? Well, the amount of work that you do depends on how much energy you have stored at the beginning and how much you have at the end. And it's the change in the amount of energy in your system. Right? That's how much work you have. You can choose to measure this from wherever you want, right? You can choose to measure Y from here. You could say, you know what, no, I'm going to use this point and I'm going to measure everything from here. Okay? It doesn't matter. It's completely arbitrary. Right, so what if I measured all of my positions from here, right? Well, then y1 would be 0, and y2 would just be the new y2, right? This distance here, we'll call it h. And that's just going to be y2 minus y1, right? That's all it is, right? We can measure this from wherever we like, right? And certain times you'll notice that I, being the lazy person that I am, will always pick my datum to be in line with where my either start or my finish is. Because then one of my work terms, or one of my energies is 0. Right? If this is where I'm measuring things from, there's no potential energy at this point, right? And having zeros in equations is nice, because then I don't have to worry about that term. Right? So we can make choosing where to measure from can make things easier for us. Right? That's the point. And it's completely arbitrary, and it's completely up to you. Right. What about units? Right. You guys haven't had Professor Tom Ford or anything yet, have you? No. Well, the Tom Ford principle of units says that you will undoubtedly forget about how important units are at some point, right? Being able to do units is really important. So what units are we talking about? We're talking about U times meter. That's going to give us a joule, right? In SI, we really don't like English units of energy because you got to talk about BTUs, and BTUs don't really mean anything to anybody unless you're buying an air conditioner, right? So we're probably going to stick mostly with SI. It's just cleaner, to be quite honest. Okay. Do you have any questions? You guys are right so far. Let's talk about potential energy, right? We haven't even talked about kinetic energy yet. That'll come later. But the way that we define this to start, right, is just due to potential energy.
And that's the reason that we're just looking at WY.
Right, because remember, it's all, potential energy due to gravity is all about where we are in the gravitational field, right? Based off of some random point that you pick to measure. That's what it is. So there's two flavors of potential energy that we're going to consider in this class. There's gravitational, right? V sub G. But there's also spring potential energy, right? We'll get to that in a second. Let's talk about this, right? So previously, we have an expression for potential energy of a body with respect to gravity that's only valid when the weight of the body can assume to be constant, right? Well, if we use this complicated equation, we can come up with work from 1 to 2, right? And what is this really? This is the amount of work that celestial bodies do on each other, and we're not going to talk about it after this, so don't worry about this equation. So if you're talking about planetary mechanics, the amount of work that the moon does on the Earth and the Earth does on the moon is calculated using this. We're not going to talk about it. So we could come up with a potential energy due to gravity, right, which is equal to the weight times the radius of the large one minus divided by the radius of the small one. Yeah, okay, great. Let's talk about spring potential energy, because this seems way more applicable to the other way, right? All right. How much work does a spring do? That's 1/2 kx squared. How much work does a spring do? The spring when traveling from point 1 to point 2. And so here's point 1, here's point 2. We'll capture this much work. I want you guys to notice something, right? Algebraically, this is the same as this, right? And it's the same as this. Same deal with potential energy due to gravity, right? We could have stripped out our common terms and we would have been left with 1/2 of the weight, or not 1/2 of the weight, sorry. The weight times the change in height, right? Weight times the change in height. Okay, so look, right? I'm talking about the work, I've got the work from 1 to 2. That's going to be 1/2 kx1 squared minus 1/2 kx2 squared, right? So here's my force, right? Here's my force, it's linear. Turns out that work is the area under the force curve, right? Which means it's the integral. We're not going to really do much of that. Potential energy of a body with respect to the elastic force, or V sub E, right? So spring potential energy will be written as V sub E. And we have VE is equal to 1/2 kx. And you're going to measure that from wherever you want, really, right? Nope. Spring, you have to measure typically from the free length, right? Because when it's at its free length, it's not storing any energy. When it's at its free length, it's not storing any energy. Right, that's what this says here. This equation is only valid if we are measuring from one position. If not, we have to account for any preload that is in our spring. Okay. You guys have any questions on potential energy due to gravity or elasticity? So let's talk about conservative forces, right? What is a conservative force? Why do we care? Well, conservative force is a force that is independent of our path, right? So what does that mean? Well, the concept of potential energy can be applied over a path, right? And if we travel this path and we come back down and we start where we finish, right? This goes up to 2 and down to 1, right? Or it can go all the way around like this. It's considered to be a conservative force if we can close the loop. Okay? If we can close the loop. It doesn't matter what the path is, but if we can get back to the beginning, right, then it's conservative. Why? Because no work has been done. Right? If you're not doing any work, then you're a conservative force. Right? And this is a fancy way of saying this. This symbol right here, that means the path integral. So take the integral over the path. And if the integral over the path of f times dr, or the force times the change in distance, or force times distance gives me work, if that's equal to 0, then we're good, right? We have a conservative force. We have a conservative. So conservative force does no work. This is going to be important when we talk about conservation of energy, right? Because if a conservative force does no work, then if U from 1 to 2 is equal to 0, then what does that mean? Well, that means that the amount of energy we have when we started has to be equal to the amount of energy we have when we finish. We can look at this, and this is the gradient of U. We're not talking about the what we care about is what makes it a conservative force. And a conservative force is one that does no work over a path. Okay. All right. So what do we have here? Work of a conservative force, U from 1 to 2 is equal to V1 minus V2. All right. V1 is all of the potential energy at state 1. V2 is all of the potential energy at state 2. This could include gravitational and spring, or just one, right? It could be both. Do I have a spring that's high up, right, above my datum that I'm measuring? This could be both, right? So the concept of work and energy tells us that U from 1 to 2 is equal to T1 minus T2. Okay, what's T1 and T2? That's our kinetic energy. So when we have conservation of energy, in this class, conservation of energy, tells us that the kinetic energy at the beginning, at state 1, plus the potential energy at state 1 is equal to the kinetic energy at state 2 plus the potential energy at state 2. Right? So the total energy, E, is equal to the kinetic plus the potential energy, and that is going to be constant for our systems, right? So when we look at a problem, if I had a ball, right, at the top of a hill, and we'll call this state 1, and then it comes down here, and that's state 2, right? Conservation of energy, if we ignore friction, right, because friction is not a conservative force, if we ignore friction, the amount of energy that I have in potential at the top of the hill has to equal the amount of energy that I have in kinetic at the bottom, right? Conservation of energy. When a particle moves under the action of a conservative force, the total mechanical energy is constant. Now it's important that we recognize it as mechanical energy, right? This means that we're only talking about potential and kinetic. There are many other kinds, right? There's sound energy, there's heat energy, there's collision energy, right? Which is typically sound and heat together, right? Light energy, if you wanted to go in there, right? This assumes, what we are assuming here is that all of our energy in our system is mechanical, which is not really the case, right? But it works for us getting an idea of how things are going to play out if we make certain assumptions. So I guess there was a picture there that I shouldn't have drawn over. Sorry. Here's a pendulum. This is a pretty nice pendulum, right? People like pendulums. What do we have? We have A1, A2, and A3. This pendulum is swinging through here, right? At the very top, before I release it, it has no kinetic energy, right? It starts from rest, it has no kinetic energy. What's kinetic energy? It's 1/2 mv squared. 1/2 mv squared. What are the units on kinetic energy? It's a great question. I'm glad you asked. Joules, right? So you can just add it to potential energy. It doesn't matter, right? They have the same units. Remember, energy is what we call, it's a scalar quantity. It's all about the amount of energy you have. It's not about whether it's positive or negative. It's all about, I have this total amount of energy in my system. Energy can neither be created nor destroyed, right? It can be transformed from state to state. So if I start with a certain amount, I have to have that amount at the end, right? That's the whole idea. So if I swing this pendulum, right? And I'm using this point here as my datum, at the very bottom, right? I start here from rest. I have no kinetic energy. I have everything in terms of potential. Right? I move down here. I can set this up where T1 goes away. Right? So that's my total energy. What about at state 2? Well, at this point, I have no potential energy, right? I'm at the very bottom. I'm back at my datum, right? My datum is where I'm measuring everything. If I am measuring from there, the distance that I move from there is 0 now when I get down. So I have no gravitational potential energy, right? I only have kinetic energy at the base. Right? And then we swing back up and we would find that, when we get up to 3 again, we again have no kinetic, but just potential. Think about it this way, right? If you swing it, at some point it's going to stop and change directions, right? And when it stops, that's when we have 0 kinetic energy, right? Friction forces are not conservative. We talked about this, right? So the total mechanical energy of the system involving friction decreases. Does this mean that energy is not conserved in real life? No. It just means that the way that this is set up, we're talking about mechanical energy. We're not talking about heat, right? We're not talking about sound. We're not talking about light. We're just talking about things due to mechanical energy. Right? So when you include friction, you're actually going to find out that you cannot write this. You can't use this equation, right? Because you're actually going to lose some energy to heat due to friction. When you guys take the thermodynamics class, that's when we go into the first law, right? And how energy conservation works across multiple, or how do we tie heat and mechanical or electrical energy together. That's not this class. This class we're going to focus only on mechanical energy, right? So only potential due to gravity and springs, and only kinetic energy. And mechanical energy is dissipated by friction that we talked about. All right. You guys comfortable with conservation of energy? You have any questions on conservation? Okay. Let's try this. This one looks fun, right? Dr. D, your idea of things that are fun is weird. True. Very true. All right, so let's look at this. What do we have? Sorry, I'm gonna find this problem in my notes. There it is, maybe. All right, so what I have. 20-pound collar slides without friction along vertical rod as shown. Right, so we're gonna start at the top, right, because that's state one, and then at some point in time, we end up moving down here. The spring attached to the collar has an undeflected length of 4 inches and a constant of 3 pounds per inch. So in English units, right, in English units, we can talk about energy as foot-pounds. So if the collar is released from rest at position 1, determine its velocity after it has moved 6 inches into position 2. Let me see something that's going on here. Oh. Okay. So I want to talk about this, right? For what should we be doing for this, right? What tool are we going to use? What kind of problem is this? Is this a Newton's law problem, or is it a work energy problem? And how can we tell the difference, right? Right now, what we're trying to develop is our work energy toolbox, right? In the toolbox, currently we have kinematics, we have Newton's second law, and work energy. So what do you guys think this is going to be? What kind of problem? What are we looking for? What are we looking for? What were we asked to find? What were we asked to find? Velocity. We're asked to find velocity, right? What? So does Newton's law allow us to find a velocity? What is Newton's second law? So what is Newton's second law? Does it allow us to find a velocity? What was that? So, no, you're thinking of distance equals rate times time, right? Which is a kinematic equation, right? Which is not going to be useful here because we're not told anything about how long this takes. So we don't have anything telling us about time. So kinematics is off the table, right off the bat, right? Because we need to know at least something about the time scale of the problem. What's Newton's second law? We use it in the last problem that we talked about, right? Maybe you got 3 laws. You never got like a 33% chance. There's only one with an equation. So. Yeah, sum of forces mass times acceleration. Is there a way for us to easily get velocity from that equation? There's massive velocity. There's acceleration of velocity. Kind of. It's a change in velocity. But then we have to take the integral of it, and I'm again not giving any time scales, right? So it's not really worth it. So what we're going to do here, right, is we're going to use work and energy. Let me ask you this, right? For work and energy, do you guys see any non-conservative forces on this weather? No, there's no friction. We're told that things are frictionless. We have got a spring. Right? So what we're going to do is we're going to draw a state diagram for these types of problems. Instead of a free body diagram, we're not drawing the forces per se. There are going to be some forces that we draw on there, but this is not a full-on free body diagram. This is what I call a state diagram. Because we're going to draw what's happening at state 1 and what's happening at state 2. Okay. It essentially boils down to 2 free body diagrams that work together. But we'll see what I'm talking about in a second. So, all right, for this, if I'm going to do my state diagram here, right, which is just essentially a free body diagram, state 1 is what? Here's my collar, right? What forces do I have on this collar at this point?
Gravity.
Yep. Got the weight. What else? And spring. Let's call this Fk at state 1. Right. Well, let's draw state 2 now. What forces do I have at state 2? At state 2, right? Because look, it's pointed back at some angle. I know that this distance here is 6 inches. What else do I have? We got one more point there, right? That was on the other one. We still have to wait. Right? So that's a state diagram. We have our forces, we have that distance, we can see what it looks like in both cases, right? So like this. I'll get this out of the way. Right, notice I put 8 inches on the first one here. I have did a bad thing on that one. I put my coordinate system. Right, let's fix that. Okay, got that. So for work and energy problems, we want to get an idea of how this is moved, right? We want to know what forces are acting on it, how is this moved, right? Why? In general, in its most general form, work is just the force times the distance that we've moved through, right? In its most general form. That's good. So if we're looking at this, right, we have a few things on here that we know. We were told that the weight was 20 pounds, that the weight of the collar was 20 pounds. Remember, it just said 20 pounds. It didn't say 20 pounds mass. It didn't say 20 pounds force. It just said 20 pounds. Whenever we're given just it in pounds, we assume that that is a weight. You will be told specifically when you need to assume it is a mass. Notice I calculated the mass up here. I divided by 32.2, and if you calculate the mass 20 pounds is 0.6211 pound mass. K was given as 3 pounds per inch, and delta is 4 inches. What's delta? Delta is the undeformed length of the spring. Right, so that little snake-looking character there, the music note, right? That's delta. It's a lowercase delta. That's my undeflected spring length. Why is that important? Because remember, I've already at 8 inches, right? Already at 8 inches. Which means I've got preload in my spring. Okay, so I have to account for that in terms of how much energy is already in the system. So we can write equations, right? And what we're going to do is we're going to look at each state. Right, I'm going to start with state 1. And if I start with state 1, well, I know that I have gravitational potential energy and I have elastic potential energy, right? But notice, I put my datum very cleverly in line with state 1. So everything's being measured from state 1, right? And if everything's being measured from state 1, then what? Then I don't have any potential energy in state 1, right? Because it hasn't moved in the gravitational field. That's why the gravitational potential energy is 0, state 1. What about my elastic? Well, the elastic potential energy at state 1 is just 1/2 of x1 minus delta squared. Remember, right? It's normally 1/2 kx squared, right? But x is how much I have moved from the undeformed position. So I've got 4 inches in there already that I've moved, right, from the undeformed position. I've stretched this by 4 inches. So there's some amount of energy that's already being stored in the spring. How much is it? Well, it's 1/2 times 3 times 4, which is 24 inch-pounds or 2 foot-pounds, depending on which units you want to use. Okay. For this, is everybody okay so far with what we did for state 1? Maybe? Maybe? Sarah. That's state 1. State 1. We now have to figure out the stuff for state 2, and this is where things get fun. He says. All right, so I need this V sub 2, right? Because we know that there's going to be some potential energy. I've got potential energy due to both gravity and elasticity. Right? So what's my gravitational potential? Well, 20 pounds and I've moved it -6, right? I've moved it down below my datum by 6 inches. So I end up with -120 inch-pounds. Okay. What about my elasticity? What about my spring energy? So I need to figure out how much I moved, how much I've extended this spring, right? Come on. Well, how do I figure out that this is 10? Right? Good question. How do we figure out that that's 10? Well, check this out. Wait for it. Yep, right triangle, right? So you can do Pythagorean theorem. Or you can say, well, that's, if I divide both of these by 2, right? This is 3, 4, this is a 3, 4, 5 triangle, right? Which would make this 10. Or you do Pythagorean theorem. Right? Pythagorean theorem tells us that 8 squared plus 6 squared is equal to c squared square root of trig. Right? Trig makes a comeback. So that's how we figure out that that's 10 inches. So you can figure out that I've got 54 inch-pounds here. So the total amount of potential energy is the elastic plus the gravitational, right? So 54 minus 120, which gives me negative 66 foot-pounds, which is negative 5.5 foot-pounds. Okay, so converting from inches to feet, right, you just divide by 12. 1 foot for 12 inches. Everybody with me here? We're all good?
That WY equals what?
Yes. W times Y. That's the weight times the height. Right? Is equal to 20 times negative 6, right? Because I've dropped it 6 inches below my data. So it's a negative. All right. Write this a little bit nicer, I guess. Okay. Everybody with me on this so far? Are we tracking? Do I need to step back? Does anybody have any questions? Yeah. Go. Which? This guy right here. So that's VG, right? That's the gravitational potential energy, right? What's potential energy, right? It's mass times gravity times height, right? Mass times gravity is just the weight, and the height is that y distance. So it's just W times Y. Okay? Does that answer that, or?
Is that other one?
Yeah, it's VE2. So. Guys, man, I'm gonna have to go, but I'm gonna have to take a night class on penmanship. Jeez, you guys are harsh. Dang. Fine. You gotta be that way. Yeah.
Would you use the 0.62 like in a pound meter?
Yeah, pounds mass. So let's read that. M is equal to point. That's worse somehow. Mass is equal to 0.6211 pound mass. Where did I get that? I divided this by gravity, right? So W divided by G is equal to M. So it's 20 divided by 32.2. Right? So in foot, foot-pound second. Okay. And so the very last thing that we need to do after we've done all of our potential energy, right, is what is the kinetic energy at state 2? Right? So what is kinetic energy? Is 1/2 mv squared, right? I don't know what the velocity at state 2 is yet. That's what we're looking for. But I do know the mass, which is 0.6211, which is just the weight divided by the acceleration due to gravity. This gives me that my kinetic energy at state 2 is equal to 0.311 V2. So now what? Well, now we use conservation of energy, right, to figure out, to solve for V sub 2. What is conservation of energy? Well, the amount of energy I have at state 1, so the potential plus the kinetic at state 1 is equal to the potential plus the kinetic at state 2, right? The amount of energy I have when I started is equal to the amount of mechanical energy I have when I finish. That's what it is. So let's look at that, right?
What's the SI equivalent of in pounds or pounds?
Oh, foot-pounds is joules. Conservation of energy, right? T1 plus V1 is equal to T2 plus V2. So 0 plus 2, right? Because I have everything in foot-pounds. 0 kinetic energy, 2 foot-pounds potential energy. Is equal to 0.311 V2 squared, right? Those are kinetic at state 2 minus 5.5 potential at state 2. And then you can solve that, right? So let's let's look at this over here. I want to solve this. What do I end up with? Well, I got to add 5.5 each side. So that gives me 7.5 is equal to 0.311 V2 squared. Right? Okay. Divide by 0.311. Can't do that one in my head. .189. Take the square root. That's not 7.189. I don't know what I did in my calculator to make it get 7 point, well, it should be 24.12, right? 7.5 divided by 0.311. Somebody else double check that. 24.12. All right, cool. Yeah, that'll do it. So if you take the square root of that, then you'll get plus or minus 4.91 feet per second. Why is it plus or minus? Because it's a square root, right? So think about it this way, right? It depends. If it's fall, depends on which direction you're moving, right? I could have pulled this 6 inches above or below. It's going to get the same velocity, right? Because it's the same system. So it depends. Am I moving positive or negative direction, right? One's going to be pulling to the left, one's going to be pulling to the right. The square root gives you, it's the same reason why we get positive and negative time, right? Which one is appropriate? The positive one or the negative one? Underline the negative one, right? Why? It should be pulling back towards, I'm sorry, because we let it go, right? And it's dropping. It's moving down. Right? Likewise, though, you could have pulled it down 6 inches and let go. Then it would be moving upward, right? Because it is on a spring. So it's going to oscillate. So both are correct. It depends on which way we're moving. We're moving up or down. Both are correct. But we were told specifically that it is in the downward direction. Okay. All right. You guys have any questions on this one? Maybe, maybe not.
So a lot of people
Bigger like this. The one that, like a capital. I use the capital V as the total. right? So all of the potential energy at state one. Right, so V sub one is equal to V gravitational at one plus V elastic at one, right? That's just the notation. And so this script V, all right, so let's go over the V's. This is an important one, right? So if you see this V, right, that looks like a weird upside down A, that's volume. It's volume. This is potential energy. And the script one is velocity. Okay, that's generally when I write things. I realize that script one looks like maybe an R or an N, depending on what day of the week it is. I get it. Apologize in advance. But that's typically right. So volume, potential energy. Velocity. There are a lot of different V's in engineering, guys. A lot of different V's. All right. Any other questions? No? All right, well done. You guys, I wouldn't want you to feel left out, so you guys can try this one. And so you guys can work in your table groups if you want to discuss it. It's fine. If you guys, Julian and if one of you wants to move, you can go do that. So what is this, right? What is this guy? Well, I've got a half-pound peg. Right? I've got this half-pound Pez pellet here, and I've got a sweep track set up, and I'm going to push it back on the spring, and I'm going to let it go, and I want it to get around the loop because it's COVID and I'm bored at home, right? That's basically what happens. You have to think of ways to entertain yourself. So a half-pound pellet is pushed against the spring and it is released. So I'm push it, it's going to release, it's going to go around. I want to know what is the minimum force. Right? What is the smallest deflection, not the minimum force? And it's the same question, but we're going to frame it as the minimum deflection. The smallest deflection of the spring for which the pellet will travel around the loop and remain in contact with it at all times. So what is the minimum amount of energy I have to put into this spring, right, to make sure that the Pez gets all the way around the loop? You guys start that one up.
Yes. Yes. Oh, sorry. That's the velocity of getting. Now it's gonna go. It's not good, the last one. The first day, one half. It's going to the 25.
Oh, yes. Not too sure either, right? You know, those things divide by 12. But, you know, the pound like was throwing me off. The way. But, yeah, I do. Oh.
Yeah. A little bit off. Mm.
Well, we converted the three pounds per inch by dividing by 12. Is that how you do that? Everything else is easy.
So if you want to convert 3 pounds per inch into pounds per foot, right?
Yeah.
Right? Like a multiplier as well. So another way of thinking about this, right, is if you apply 3 pounds, if you move by 12 inches, you get 36 pounds out, right? So so start with 3 body diameter, right?
Yeah, okay, I tried.
So, all right. I got 0.373 feet, or 4.5 inches. So what'd you guys do? Or did you multiply your mass by 32.2? You multiplied the pound by 0.5 by 32.2? So that's a fourth, that's the weight, right? If you want to you definitely, if you're considering energy at the top, energy at the bottom, you're on the track, there's probably dress going and remember, if you're doing Okay, let's take a few more, take a few more minutes.
usually that's what we use. Yeah, so I need like 25. Yeah. Yeah, so now I'm just all.
All right, let's
Oh, yeah.
talk about it. Talk about it. So talked about with one of you guys in your groups, right? Right, how do we start this? How do we start this? Well, we should start with a free body diagram at state 1, and we need to pick a state 2. Now, this thing has 5 different points on it, right? State 1 is clear, it's A, right? And what's gonna happen is we're gonna push on this, right? We're gonna push on this, we're gonna let it go. So we go from A to B to C to D to E, and then all the way around. But what's the most dangerous position here, right? It's D, right? And if you can make it all the way across D, then you did it, right? You're rewarded with a Pez that flies down the other side of the loop, presumably into somebody's mouth, because that would make the most sense. Right? You're gonna shoot candy into somebody's mouth. Does it make sense to me? I have 2 toddlers though, so it's a little different. Anyway, so what we do? We need to make sure that we hit this worst case scenario, right? There's a couple of caveats that come with point D. And we'll talk about those in a second. So let's start with our diagram here, right? We'll move this out of the way. We'll talk about the equations later. Let's just look at the diagram. So it's state 1, state A. What do I have? And notice I'm using normal and tangential coordinates here, right? So I'm going to push on this spring and I'm going to hold it and lock it in place, right? And if I've moved it by some distance, then I have the force Kx pointing back at me, right? I've got a normal force and I've got the weight. At some point, I reach D, right? And when I get to D, I am elevated by 4 feet, and the only 2 forces there are the normal force and the weight. But notice the normal force is in the same direction as the weight. Weird, right? But why? Well, because the track's pushing on it, the weight's pulling down, right? Our weight is ½ pound. Our spring constant is 3 pounds per inch and 36 pounds per foot. Right? Notice my datum starts on the ground. This is going to be weird, right? But let's just start this as a work energy problem. Right? Let's start this as work energy. This is going to tie in a couple of things together, right? So, all right. So I've got my diagram. Everybody okay with the diagram? Everybody see how we came up with those FPVs? Any questions on that? I realize it's drawn from left to right. You might have it drawn from right to left, which would be fine too, right? The overall goal is the same. So we're going to get our elastic spring potential energy at state A, right? So V east of A. The elastic potential energy at A is 1/2 kx squared, right? I'm going to do this in terms of feet, right? So it's 1/2 of 36 times x sub A squared. So how much I have moved that, right? And my kinetic energy is starting at 0, right? We're starting from rest. So that takes care of point A, right? What about point D? Well, at point D, the elastic potential is 0, right? We're no longer touching the spring. The spring has nothing to do with this anymore. Because the spring has nothing to do with this anymore, we don't need it, right? It's 0. But what do we have? We do have gravitational potential, right? We got mass times gravity times height there, which is the weight times 2 times the rho, or the radius, right? It's just the weight times the diameter of our loop, right? Which is twice the radius, which is going to be 0.5 times 4, which is your 2 foot-pounds of potential energy due to gravitation. But we're not stopped at point B, right? There's still potential energy. kinetic energy, right? If we stopped at point D, we would just fall off the loop, right? So there's some velocity carrying us through. So we have a kinetic energy there, right? Which we can write as 1/2 of our mass, which is 1/2 divided by 32.2, times the velocity at point D squared, which comes out to 0.008 times the velocity at D squared. So a really small amount of velocity, right? And I can put all these things together using conservation of energy, right? So the energy at point A is equal to my energy at point D, right? Which is 1/2 of 36 times x squared is equal to 2 plus 1/008, so D squared. And that's equation 1, right? So I need one more equation, right? Because I've got two unknowns there. I've got the velocity at point D and the position at point A. And this is where you have to talk about what is the minimum condition for this to stay on the track. What is the minimum amount of normal force that can be applied so that this will still stay on the track, right? So this is where this becomes important, right? So if you're looking at this, how much normal force can I put on that and still have this be on the track? 0, right? If the normal force is 0 or negative, then this will be staying on the track. And that's a weird concept to think about, right? Because look, the normal force is pushing us back. That's pushing us down, right? So don't think of it as a normal force. What if I was standing there and I was pushing down at the top, right? What if that was the case? If I wasn't pushing, if there was no force there, I would stay on the loop, right? So we're going to say that at the bare minimum, the normal force has to be 0. Okay? And we're actually going to bring in Newton's second law to talk about this now. Because we need to figure out how that works. Wait for it. Please don't do the thing. So I'm going to sum my forces in the normal direction. If I do that, I'll get the mass times the acceleration in the normal direction is equal to the weight plus the normal force. So if I am going to assume that the normal force is 0 for the reasons that we just talked about, right? At the worst case scenario, we have no normal force, right? It's worst case. Why is that worse? Because we're not touching it, right? Worst case scenario. In the worst case scenario, this is 0, so we just have the weight. Okay, so the weight's equal to the mass times the normal acceleration. But remember, a couple weeks ago, maybe it was last week, I don't remember, time has no meaning anymore, right? But we did this at some point when we talked about that the acceleration in the normal direction is just the velocity squared divided by the radius of the row, which was the radius of, not the radius of gyration, but the blanking on it right now. But the distance we are away radially from wherever we're rotating about, right? Okay, well, we know that. That's 2, right? We were given that. Our circle has a radius of 2. We can solve for V sub D, right? We know the weight, it's 1/2 pound. We know the mass, that's 1/2 divided by 32.2. We know rho, that's 2, right? This becomes VD squared is equal to 62.5. Notice, I'm not going to take the root of this. Right? And the reason is, if we go back, which my clicker won't let me do, but if we go back, our other equation is already in terms of VD squared, right? So I'm just going to substitute in what I solved for as VD squared into VD squared, right? And so once this decides to clear itself up, here we are. I've got 1/2. So this is my equation 1, right? 1/2 of 36 times XA squared is equal to 2 times 0.008 times 62.5 There we go. Solve it out. We need it to be 1.5. The key to this one, which is the trick, right? And yes, there's more often than not, when I ask you guys to do a problem, there's probably going to be a trick that we have to think about, right? The thing I wanted to highlight here is that you can bring in what we know about normal and tangential coordinates, right, to figure out what that velocity is at the top of the loop. And the bare minimum, right, we need to think about this. The bare minimum condition is when we are no longer in contact with the loop. When we're no longer in contact with the loop, we don't have a normal force, right? So the smaller our normal force is, right, means that we're not in contact with the loop anymore. At the worst case scenario, in order for us to clear the loop, we need to press by 4.5 inches. Does that make sense? It's tricky. It is a tricky problem, right? There's certainly a trick there. Now, in real life, right, a lot of the problems that we've been doing in class, right, they're just Newton's law problems, right? Or they're just work energy problems. In real life, nothing is only ever one thing, right? You can start seeing the creep in here. The last two problems we did, right? We needed kinematics to figure out our acceleration. We needed normal and tangential forces here, right? To figure out our velocity. There's a lot of different applications, and all of these things are going to start to kind of tie together and become applied at the same time, okay? You guys have any questions on this one?
What unit is it?
Feet per second, feet squared per second squared. Why is that, right? Well, because it's a velocity squared, right? And velocity squared is normally in feet per second, but the whole thing is going to be squared, right? It's feet squared per second squared. It's kind of a made up unit that has no real significance, right? But that's what it is. Okay. Is there any other questions?
So that's at 2 times 0.008.
Was that supposed to be 2 plus 0.008? Hold on, let me. Yeah, sorry, it's supposed to be 2 plus 0.008, right? It's supposed to be this equation down here. Right. So I copied it wrong. To make sure that the math is right. Good catch. But I gotta wait a second for this to clear. This should be 2 plus 0.008 times 62.5. That's the kinetic energy, right? The 1/2 mv squared, right? So this comes from the kinetic energy at point D, and this is my gravitational potential energy at point D. So we can, let me double check my math here to make sure that this, so you guys could run some numbers. Because we've already proven today that I'm bad at calculator. Right. There we go. It should be 6.7, right? Yeah. inches. No, that should be feet, right? Right. There we go. So there, right? I did that conversion, right? Feet to inches. Yep. Okay, so Julian, answer your question. Where did this equation come from? Right down here. This is what we built. Right? This whole thing. What we're trying to do, remember, is T1 plus V1 is equal to T2 plus V2. In this case, state 1 is point A, right? At point A, what do I have? I have elastic potential energy, and that's it, right? So all of this on the left-hand side, this is going to be 0. All we're left with is 1/2 kx sub A squared, okay, which is this stuff right here that I've underlined in here, right? At state 2, what do we have? Well, we've got some potential energy, right? The potential energy is due to what? Well, there's no spring anymore, so the elastic potential energy is 0. Our gravitational potential energy is the weight, or the mass times gravity times the height. What's the height? It's at the top of the circle, which means it's got to go the entire diameter, which is 4, right? Which is 4. Or, right, so we figured out that this is 2 foot-pounds, right? So that's where that 2 comes from, right here, right? So this guy right here is just this, right there. What about 0.008 V sub D squared? Well, there's some kinetic energy at the top, right? It's still moving. It hasn't stopped moving. It's still moving to the left, right? Or to the right, depending on which way it's going around the loop. Right? So it's still going to the right because it's going to come back down. How do we determine how much kinetic energy we have? Well, that's 1/2 mv squared, right? I don't know what that V is. So my mass is just a 1/2 pound divided by 32.2, right? And so that's where this 0.008 comes from, right? And so it's just us taking the total energy that we started with and equating it to the total amount of energy we have at the end, right? So we needed to figure out what V sub D was. And how we did that was by going into normal and tangential coordinates, because we know that the normal acceleration is the velocity at that point squared divided by the radius of curvature, which we were given as 2 feet. Okay, so that's where this next slide here comes from. Right, so that's where, wait for it, that's where this comes from here. Right, this whole thing that I'm underlining and doing. This whole section comes from us looking at our free body diagram as drawn in normal and tangential coordinates, right? If we sum our forces, we use Newton's second law, we sum our forces in the normal direction at point D. We have the weight and the normal force in the normal direction. The normal force we're saying is 0 because in the worst case scenario, we're no longer touching. And if we're not touching, we don't have a normal force. Okay? So we know the weight, we know the mass, we know that the normal acceleration is equal to Vd squared over rho. We know all those things we can solve for Vd squared. I didn't take the square root because when we look at this equation down here, right, remember this is 2 plus 0.008 times Vd squared. I'm just making that direct substitution in, right? I already know what Vd squared is, I'm just gonna move it in. Okay. That should come out in feet. So I guess looking back on it, right, I should have known, right? Because a half pound of candy, I mean, that's a lot of candy to be firing on the loop. I mean, it's a significant amount of candy.
So it's just 0.373.
What's up?
Yeah.
The previous answer was 0.373, but when we started talking about this, I noticed that the equation was not transcribed correctly, right? So if you write it like this, before when it was 0.373, it was 2 times 0.008 was how I wrote it originally, which is not the case. It's 2 plus 0.008. So it affected the output. Right? Okay. Okay.
And that's the X-ray, that's like a part of the spring.
Right, exactly. It's a big spring, but it's also a half pound block, right? So when I start talking about it as candy, my mind goes to like very tiny things, and half pound is actually significant. So I apologize. That's on me. I'll have to think of a better way. But anyway, you guys have any other questions on this one? Yeah, Logan. For which one? For right. So sure. So if we are going to sum Newton's law, right? Remember our free body diagram for the block. This is at point D, right? There was a normal force and there was our weight, right? So we're going to use Newton's second law, and we are going to sum our forces in the normal direction, right? Because I've decided that I'm going to use normal tangential coordinate system. Why? Because we're traveling on a fixed circular path that we know is not changing. Okay, we know is not changing. So you have a normal and tangential coordinates, right? If I sum my forces in the normal direction here, what do I get? Well, I've got my weight plus my normal force. We talked about it. We said, you know what? And the worst case scenario, we're not touching normal force is 0. That goes away. This is equal to the mass times the normal acceleration. The normal acceleration, which we talked about during kinematics a couple weeks ago, tells us we can define the normal acceleration as v squared divided by rho, where rho is the radius of curvature, which we were given as 2 feet, which is where this equation comes from. So it stems from Newton's law, and we're making an assumption about the normal force based on the worst case scenario that can possibly happen. That's what we're doing. Okay. Make sense? Ish. All right, you guys have any other questions on this one?
Where did the 0.05? Like,
The weight, did I
think it would be.
it should be 0.5. Did I mess everything up again? It's double component. All right, so I'll rework the numbers again, but watch, now it'll be 0.373. It should be off. No. I'll rework the numbers later. We'll get back to this. This was a train wreck, eh? Sorry, guys. Good catch. Hopefully, I just wrote it wrong, but I don't think that that's the case. It's wrong in the notes too. Okay. Crunch those numbers a little more. It's not 62.5 anymore, right? Comes back to the answer. I got 0.333 this time. I want to do it all the way through. Okay. So if you do it with the correct numbers in there, right? This comes out in my calculation 0.0621. If I plug that in to here and here, then I will get 0.333 feet, which is 4-ish inches. And that's what I got, which is what we had originally, basically, like 0.317. All right. Well, now that everybody's good and confused, right? Now that we've proven that Dr. D can't write numbers or do math, we'll just end class. So I think that that'll be a good point for stopping. Also, we've got like 2 minutes left, right? Do you guys have any questions aside from? All right, so process-wise, let's talk about this. Process-wise, do you guys understand the process of how to think about some of these problems, right? We'll go over in one of the next classes. Once we introduce impulse and momentum, next class, we will talk about what are the keywords that we're looking for with different types of problems, right? So how do you know something's a Newton's law problem versus a work energy problem versus an impulse momentum problem, right? So we will go over that and what you should look for in problem statements. So in general, we'll just state it now, but we'll go over it again. In general, if you're doing a Newton's law problem, you will know because you'll be looking for forces and accelerations. For work energy, you'll be looking for displacements and velocities. And for impulse momentum, you'll be looking for time that something occurred in or force. So if you're asked to find how long something took to happen and you're given a force, you should be using impulse and momentum, which is what we will focus on next class. Okay. Okay. You guys fill this out and then you can bolt. I do have office hours after class. Remember, use the Zoom link in the announcement. It's on the first day, like the very first announcement or second announcement.
So this class, the way you're gonna go for next class, the key in this question is breaking it down and analyzing the keyword and knowing what you're trying to solve.
Yeah, and I think we're gonna do a bunch of problems for free, but so like next class we'll go over like impulse, impact, how to do some problems that are multiple things, like whether certain problems you can break down into like depending on where you are in the life cycle of the problem, right? You can do impulse momentum into work energy into law, right? Kind of work through different parts of the problem. So that's kind of stuff we'll do over the next class. And then, like how to differentiate.
Yeah, I think you can really